Okay, guys, it's 1:30. We may as well get started, so you guys can have the full time to ask any questions. Somewhat more sparsely attended than I expected, but maybe everybody knows everything, so no one needs to ask any questions. I guess, do I have any announcements to make? I can't think of any. Oh, you have a little test on Wednesday, which is just a reminder. And just another reminder, you can bring two note sheets, so front and back, 2 pieces of paper, so that you can just reuse your one from little test 1 if you'd like. And it covers, I don't know if I've said this before, I think I have, it covers everything up through modern SGD. So there's no mirror descent, and today is like a combination of you guys asking questions and me mentioning some non-convex stuff. The non-convex stuff won't be on the exam. So it's everything previously, and it's mostly this stuff, so after little test 1. So it's mostly what comes Newton's method through modern SGD. There'll be a few questions from the first half as well, but focused on the second half. And the same format, I think the same difficulty, just more or less straightforward true or false questions, multiple choice questions. Next Monday, so a week from today, we have our final exam period, right? It's Monday, not Tuesday, just checking. Yeah, Monday, December 10th. We're going to hold COPS, which is I don't know what installment of COPS it is. Maybe the third installment of COPS. This stands for CMU Optimization Symposium, so it's like our class conference. And we're going to try to hold it this year to be 2 hours total. So we have 3 hours for the final exam period, but that's exhausting for everybody involved. So we're going to try to hold it to 2 hours. What that means is that I probably will not be able to look at every poster. So we've divided up the posters into me and some TAs, another group of TAs. And I'm sorry if I'm not going to be able to come around and look at your poster. If we did that, then we'd all be there for 3 hours. So, and even then, I think it'd be difficult given the size of the class this year. So for those of you who got the email about the spotlights, you guys have 8 minutes for the spotlight talk, and everybody else has poster presentations. There's an hour. The spotlights are basically going to happen 2 at the start, an hour for posters, and then 2 spotlights at the end. And we'll send an email or a Piazza post out with details about like how to set up and whatnot for that. Okay, and then the final report's due on Thursday, which is a few days after that. Any questions before we, jump in today? No, it's in Rashid Auditorium. I think that should be written down, here. So that's the big conference, that's the big classroom on the 4th floor of Gates. And we'll use probably a combination of inside Rashid on the stairwells and the walls, and outside Rashid for the posters. Any other questions? Okay, so to start us off, I figured I would show you this table that I completed, and it's linked at the bottom of the lecture notes, of our class calendar. And let's just go through this kind of quickly, and then I'm happy to take any questions people have about anything. And if there's time, I have a bunch of slides on non-convex problems that I prepared. They're not posted as part of the link, as part of the website here, because I wasn't sure we were actually going to get to them. But if you want to see the slides, just type in lectures at the end of the URL for this class, and it's nonconvex.pdf, this one here. Okay, so that's where you'll find it. All right, so let's just go through this table. Or in fact, there's kind of 3 tables. And just a very quick recap of some of the basic things you learned from methods. This has nothing to do with the convexity theory or optimality theory, duality theory. This is just the methods themselves, the algorithms. So we have gradient descent, the subgradient method, proximal gradient descent, and the stochastic gradient probably should say method, but we say stochastic gradient descent. It's four methods, four first-order methods you guys learned. What is the criterion that they each look at? For gradient, it's a smooth function f. So by that I mean it has one derivative, so it has a gradient. For the subgradient method, it's any function, but really, of course, convex is the big qualifier for everything in this table. For proximal gradient, it's smooth plus simple. So g plus h, where g has a gradient, and h is a function that's convex, whose proximal operator that we know how to compute. And for stochastic gradient descent, it's also smooth plus simple. We talked about mainly SGD in the smooth case, but if you wanted to, you could also do proximal stochastic gradient descent. It's the same as proximal gradient descent. You just replace the gradient by a stochastic estimate, and then you apply the prox operator of h. Okay, constraints. What kind of constraints can we deal with, and how do they figure into the problem? For gradient descent, subgradient method, okay, this is a bit confusing. This one I should have said constrained prox. Sorry. For gradient descent and for subgradient method, how we deal with constraints is projection. Okay, so if we have a constraint, then we take a gradient step and we project. For proximal gradient descent, if we have a constraint, then if you go and drive the prox operator, you'll see that the prox operator is itself constrained. You can think about that as h plus another function, which is the indicator, and we're talking about the proximal operator of h plus that indicator, which is a constrained prox. So that could be substantially more complicated than a prox itself. What kind of step sizes for these guys? Fixed step sizes or line search, essentially, for proximal gradient and gradient descent. And for the subgradient method and for SGD, vanilla SGD, like not the variance reduction stuff we talked about a week ago, diminishing step sizes, okay? Or fixed step sizes in either. But if you fix them, then these methods aren't guaranteed to converge to optimality. They'll converge to a point that's suboptimal by a certain amount. That depends on the step size. Iteration cost, cheap for gradient descent. You just have to compute the gradient. It's cheap for subgradient method. It's very cheap for SGD. That's the point. We're actually computing much less than the gradient. It's just a stochastic approximation. And we tend to apply proximal gradient when it's moderately cheap to apply the prox. Some proxies are expensive, but then we just usually wouldn't be looking at this method at that point, because it would probably not be worth it if the prox was so expensive. And that's because it has just first order convergence. So the convergence rate for proximal gradient and for gradient descent it's sublinear, so 1 over epsilon in the kind of vanilla set of assumptions, which is just that the gradient is Lipschitz. We can use acceleration to get it to 1 over the square root of epsilon, which is optimal for first order methods in that setting where the gradient's Lipschitz. And under strong, if we additionally assume strong convexity, it becomes linear, so log 1 over epsilon. Okay? For both the subgradient method and stochastic gradient descent, it's 1 over epsilon squared. So remember, we learned that with SGD, even if we assume strong convexity, it doesn't escape the sublinear realm. It just moves to 1 over epsilon. Okay, that was one of the reasons for looking at variance reduction. Okay, here are our second order methods we talked about. Newton, Berry method, primal dual unitary point method, and quasi-Newton. These were, maybe the... there's also proximal Newton, which I think I'll put in the next slide, but I put these 4 here. So each of these assume that the criterion function has 2 derivatives, so we can compute its Hessian. That's the assumption. What kind of constraints can we deal with? In Newton's method, we can deal with equality constraints, right? That just changes the Newton step. We have essentially an expanded linear system that we use in order to perform the Newton step. So that was sometimes called solving the KKT system because it came from the KKT conditions. So those are no problem, equality constraints. For the Berry method, we can deal with equality constraints and we can deal with inequality constraints if the inequality constraint functions hi have 2 derivatives. Because remember, what we do is we essentially form a log barrier and we approximate the indicators that represent these constraints by a smooth function in the criterion. And we apply Newton's method to that smooth function, which is why we need these to have 2 derivatives. Okay, same with primal dual interior point. As long as the inequality constraints functions hi have two derivatives, we can apply primal dual interior point. And both of these methods handle equality constraints, just because then you do an equality constrained Newton step. Okay, it's no problem. Quasi-Newton is unconstrained as we learned it. Okay, if you have constraints, even equality constraints, it becomes more complicated. So we just talked about unconstrained quasi-Newton. And I'm not really aware of work that combines quasi-Newton with something like a barrier function. I'm not sure what to say about that case. So let's just think about this as being unconstrained as we learned it. Okay. Optimization parameters for Newton and for quasi-Newton, we have to choose the step size. And for Newton's method, we used line search, right? And what we know is that line search will start returning a pure step size, so t equals 1, at a certain point, which is called the quadratically convergence phase. For quasi-Newton method, we use line search. For the interior point methods, that's the middle two columns, we have a couple of parameters. We have the step size that we have to use for the inner Newton step. So that's typically done by line search. And at the outer level for barrier method, there's what we call the barrier parameter. That's what takes, remember, if we had a term that looked like t times f of x plus phi of x, where this was the barrier function for the constraints, then somehow this seems very zoomed in. Then we have some parameter that we use to update t, right? Where this mu is what we call the barrier parameter. And it's bigger than 1. Right? So we increase t to put more weight on the criterion. Well, don't confuse this t with the step size. Sorry about that. That's not the step size of Newton's method. That was just, that's why that was so weird. Sorry. Okay, better. For primal dual interior point method, we have the same parameters. We have this mu, and we also have the step size, but we don't think about, there's no distinction between inner and outer iterations. You take one Newton step, and then you update this barrier parameter with, then you update the weight on, let's say, the criterion, or we move the perturbed complementary slackness condition closer to complementary slackness, which still involves t. We do it by multiplying by something like this, some mu. So those are the optimization parameters. Iteration cost, it's moderate to expensive with Newton, because we have to compute the Hessian itself and then solve a linear system in the Hessian. If we talk about one iteration of the barrier method, then that's actually, remember, solving essentially this problem entirely, two conversions, with Newton's method. Because we have this distinction between outer iterations or iterations and these inner iterations. So one outer iteration is very expensive, right? We have to run Newton till conversions. So we have to solve this smooth problem. For the primal dual interior point method, there's just one level iteration. So one iteration is just one Newton step. So it's going to be the same cost as whatever we encounter for Newton. And for quasi-Newton, it's better, right? Because our updates are designed to help us solve a linear system in an approximate Hessian efficiently. And the two updates we learned, which were DFP and BFGS, they both were themselves quite cheap. They were rank 2 updates, so that means we could move from solving a linear system in the Hessian at one iteration to a linear system in the Hessian at the next iteration. These are all approximate Hessians in just order n time, because it's just a rank 2 update. So how fast these things converge? Well, it's local quadratic for Newton. For quasi-Newton, it's local superlinear. So it's not quadratic, but it's better than linear. So it's somewhere in between linear and quadratic. So in between log 1 over epsilon and log 1 over epsilon. This being extremely fast, right? This is like, for practical purposes, this is like a number like 5 or 6. And for the interior point methods, they were linear. Okay, log of 1 over epsilon. And for the primal dual interior point method, there's some, I think, evidence that it behaves superlinearly and converges a bit faster than that, but the standard theory puts that at a linear convergence rate. Those are our second order methods. And the last slide is on our kind of specialized methods, although I threw in proximal Newton because it was left over from the second order methods. So proximal Newton, it's similar to proximal gradient, okay, except for we're going to be looking at functions which are of this composite form, g plus h, where g is twice smooth, so it's two derivatives. And h, we have to know it's we don't have to know a scaled proximal operator in h, which means that if you give me an arbitrary quadratic plus h, I have to be able to solve that. So we use line search for that, and each iteration is expensive to very expensive, because solving a quadratic plus h, if that quadratic has a dense Hessian, could be very expensive, but it converges at a local quadratic rate, so we don't expect to do this many times. Okay, so it's the natural extension of proximal gradient to second order methods. And these were our specialized methods, coordinate descent, ADMM, and Frank-Wolf. They all had slightly different setups and different strengths. Coordinate descent, we looked at functions that were smooth plus separable. So this h had to separate into a sum of hi of xi. ADMM was a function that was block separable. So the criterion had to be something like g of x plus h of z. And Frank-Wolf required a function for the criterion that was smooth. We had to take a gradient. Constraints, they all have play a different role here. For coordinate descent, okay, we can handle constraints as long as they're separable. If we have a constraint on each block, like xi, that's no problem. That just goes into the coordinate-wise minimization. If there's a constraint on all of our variables that doesn't separate into constraints on each of the blocks, then we can't handle that, because that's not smooth. We can't write that as a smooth function. Right? The indicator representation of that is not smooth. So we just generically can't handle such constraints with coordinate descent. You can handle separable constraints. For ADMM, we always have equality constraints. That's just an assumption about the method. And typically, if the problem is unconstrained, then we introduce equality constraints in order to apply it. For inequality constraints, if we have a constraint on, let's say, x or g or z, then that just goes into the ADMM update for x and for z. And remember that the ADMM updates were actually proximal operators in the most common case, or they were scaled proximal operators in the more general case. And so it just becomes a constrained prox or a constrained scaled prox if we have a constraint on x and or on z. Frank-Wolf, there is a constraint by assumption. Right? We assume that it has a constraint, and the constraints are always compact sets for Frank-Wolf, because we always minimize a linear function over the set in order to get the update. How about optimization parameters? So one nice feature of coordinate descent is that it's the only method that we've learned that has no optimization parameters whatsoever. Right? There are none. You just perform repeated coordinate-wise minimizations. For ADMM, we have the augmented Lagrangian parameter. And for Frank-Wolf, there are the step sizes. Okay. ADMM is also unique in some sense among the methods we learned for its optimization parameter rho, because we don't have a good way of choosing this. So in every other case, we had something like line search to choose a step size. For coordinate descent, we had no optimization parameters. For ADMM, we have the augmented Lagrangian parameter, and we have no, let's say, theoretically justified way of choosing this. It's something that affects convergence that we just have to set and trust. There are more or less heuristic ways of choosing it that I mentioned, but they don't come with convergence guarantees. Okay. Iteration cost, it's hard to really say in general, but they're all so coordinate descent can be anywhere from cheap to expensive, and same with ADMM. It depends on your setup, right? I could take any problem and talk about applying coordinate descent to very big blocks, that'd probably be a bad idea because the updates would be very expensive. So we tend to apply it in situations where the updates are cheap and the blocks are just of size 1. So we're doing actual coordinates. In ADMM, we tend to manipulate problems to take a certain form such that the updates are cheap. They can be expensive, but then you probably shouldn't be using ADMM because these both have more or less first-order convergence. And Frank-Wolf, we've seen it being on par with gradient descent or projected gradient descent and possibly even cheaper. Right, that was the point of that lecture, is that its iterations can be cheaper or simpler than projected gradient, so they're not going to be very expensive. The convergence rates, I just wrote same as proximal gradient because that's all the theory says, really. But there's a little bit of a difference in practice. ADMM is kind of similar in practice to proximal gradient, which is what we saw. Coordinate descent can be faster, which is also what we saw. And Frank-Wolf, in my experience, can be slower. So the theory is kind of loose here. There are probably some papers that refine the analyses, but I don't think, and there's no global understanding of somehow an ordering between these methods and a first-order method like proximal gradient. Okay, so that was an overview.
So if you were like, you had a problem you were solving and you had to pick a couple of those, would you just go ahead and implement all of them and just pick the one that solves the fastest on some data set, or how would you go about choosing?
That's a good question, but I think somehow I would need to know more about the problem. So if you're saying a problem in which all of these applied?
Yeah, or I guess just in general, like when you have more than one method that fits the problem, how do you pick the fastest method? When there's kind of this hand-wavy way of saying like some are faster than others.
Yeah. So I guess there are a bunch of considerations that we might have, right? So this is not supposed to be a decision tree because I don't think I could draw this on the spot. But there's this kind of maybe first way of thinking which I would look at, which is the Hessian structured or not? So by structured, I mean, if I write down the Hessian mathematically, could I think about solving a linear system in that Hessian faster than I could for a dense system? So if the Hessian has some specific structure, like if it's banded, or if it's sparse, or if it's circulant, or one of many other kind of things that I know there are fast linear systems solvers for, then I would think about a second order method. Otherwise, I'd think about a first order method. But this is not the only consideration. You might also ask yourself something like / do I need high accuracy solutions? Because if you do, then that's also the strength of second order methods. Okay, so within first order, I'm considering things like these methods to be first order: coordinate descent, ADMM, and Frank-Wolf. So then, I don't know, you could ask yourself something like, so some considerations that would lead me towards choosing something like ADMM is, for example, can I distribute my computation? Or another axis is somehow, do I want to solve an extension of my problem? Meaning, let's suppose you solved your problem and then somebody said, that'd be a really good idea to add this to the criterion or to add this constraint. So ADMM is very good at that. If you add a little bit to a problem and you know how to do the projection, let's say for projected gradient descent, you could ruin it. But ADMM often, because of the flexibility we have in setting up the problem, we can handle kind of lots of variance on the problem as well. And it's good with distributed computation. Coordinate descent, I should also say, we didn't talk about this, but actually you did it on your homework. And there's a line of literature I didn't cover on parallel coordinate descent that's also possible. It's just less studied than parallel ADMM or distributed ADMM. So you could also apply parallel coordinate descent. Okay. So now I guess I would think about applying. So here would be stuff like projected gradient descent, maybe accelerated projected gradient descent, coordinate descent, or stochastic gradient descent, right? And Frank Wolf would be in here too, but I personally do not tend to use it much in practice. It's somewhat of a matter of simplicity now for me. To get coordinate descent to work fast, it requires a very kind of careful implementation. So if I was really trying to write code that was, let's say for my own experimental purposes, and I just wanted to see whether something worked, I would probably not implement coordinate descent. Because for that to work, I would need to figure out how to go from one update to the next in a rather kind of minimal way in terms of the computation. So, I don't know. Let's say, do I want a simple implementation? I might go for the gradient methods. So I would use projected gradient descent or SGD. Otherwise, I'd use coordinate descent. And, sometimes this is not possible because I just don't know how to drive the coordinate updates, right? They don't have a closed form. So there's another access like, do I know the coordinate descent updates in closed form? And then the last thing is just like, SGD versus projected gradient. That's probably more or less a question that's answered to you by what data set you have, what size data set you have. So I would say SGD if I need to. Just because maybe it's too large. Truthfully, this is not supposed to reflect like a very, I don't know. I didn't put a lot of thought into this. I just kind of did this now. So I wouldn't, if you ask me again tomorrow, I might reorder this. But I guess at least if you didn't think about somehow this actually dictating a flow, you at least see the considerations that would go into it. Right? Maybe you would weight some of these differently, and so the order of the nodes would switch. And then like everyone else, I like coordinate descent, so I don't mind spending a little extra time to make something faster. I just think it's a neat method. I like the primal dual interior point method. I think it's an interesting method to me, so I tend to think about those things. I tend to look at a problem and think, I tend to spend a lot of time thinking about the structure, whether the structure has Hessian, whereas somebody else might give up and say, it's not worth it, right? So it's just a matter of, I guess, what methods you like as well and you're comfortable with. I think a good thing about optimization from the operations research perspective is that it doesn't actually matter. Like if you chose the wrong algorithm, you just wait longer, right? So as long as somehow you're not choosing an algorithm that's not convergent, from the operations research point of view, the solution is well defined. We're going to get to it. From the ML point of view, that's not so clear, because we have this really weird interplay between algorithm and like estimate, right? So another addendum is like the choice of algorithm now for ML applications could actually influence the kind of quality of your estimator. So it's a consideration. This kind of consideration for operations research, you probably could ask somebody in a business school or an operations research department, and they would have a very clear pecking order for these methods. But I doubt somebody in ML will be able to tell you something so concrete because of that. We don't tend to solve things to optimality, and then because of that, what we choose affects our estimator. Anybody else have comments or questions or anything else? Yeah.
As for convex problem, there should be a solution set, a unique solution set. But in practice, it seems that different methods with convergence guarantee get a different solution. How do you consider?
So for a convex problem, just to remind you, convex problem implies, maybe this might be a little test question. I can't actually remember. Convex solution set. So not a unique solution, but it means the set of solutions is convex, right? For example, like this function is convex if I didn't curl that thing around too much. And this is the solution set. So you're saying in the case that the solution is not unique, but the problem is convex, different algorithms converge to different solutions? Yeah. That doesn't necessarily bother me, but here's one. I mean, that's certainly going to happen because different methods, if the solution is not unique, will approach the solution sets from different directions. But here's kind of one hack or one popular heuristic. Suppose I have a problem. We can abstract out to this form, and it's convex. The solution is not unique, and I'm worried about that because I want to make sure that my algorithms kind of converge to something that's consistent. Let's say, I don't know, across runs or whatever. So one hack, but it can be formalized in some kind of, at least a pseudo-rigorous way, is just to add a tiny bit of L2 regularization to the problem. So for epsilon is small. This immediately makes the problem strongly convex, right? Whatever this was, the criterion is strongly convex. Its strong convexity parameter is epsilon. And now the solution is unique. And if I send epsilon to 0, so let's say x star sub epsilon equals argmin. It's just equals because the solution is unique. As epsilon goes to 0, here's my claim. I don't actually know under which conditions this is true, but I'm fairly certain I could write down a proof that didn't assume much. As epsilon goes to 0, x star of epsilon approaches the minimum L2 norm solution to the original problem. Okay, so maybe there's one thing worth commenting here. If you look at the solution set to this problem, it is convex, right? That was what we said. So let's say X is the set of solutions. So this capital X is a convex set. Now let's look at this problem. Minimize, let's say the squared 2 norm, doesn't matter, because the squared 2 norm and the 2 norm are going to have the same minimum. Minimize the squared 2 norm over all x in the solution set. Does this have a unique solution? It must, right? Because this is convex. That's strictly convex. This thing has a unique solution, which means that there is a unique solution with minimal L2 norm. So in fact, for linear systems, like if this f of x was, quadratic, x transpose ax minus b transpose x, so the solution is a solution to a linear system. This is, there's infinitely many solutions to that, but there's one with minimal 2 norm. And that's the pseudo-inverse solution, more Penrose pseudo-inverse. But it's true in general, right? If you give me a convex problem, there's a solution with minimal 2 norm. And my claim is that you can get that by solving this problem just with a small epsilon. And if you take epsilon to 0, then under weak conditions, which I don't know I can specify now, you'll get to the minimum 2 norm solution. Does anybody know? I'm just curious what the field that studies this is called? It means the solution as I change the problem a bit. It's a very interesting field, which if there was a course in advanced optimization, I would have spent some lectures on it. It's called variational analysis. So variational analysis is the field that actually makes these kind of statements precise. As I change my problem, so now I'm optimizing different problems. I'm optimizing this for a different epsilon as epsilon changes. How does the solution set change, or how does the solution in this case change? The field that answers that is called variational analysis. It's like a cousin to convex analysis. And not surprisingly, at least not to me, or not to people who have kind of read some of his work, Rockefeller has the textbook in that field as well. So Rockefeller has a book called Convex Analysis, and he also has a book called Variational Analysis. And they're like, in my mind, the best two textbooks about those subjects. Yeah.
Norm from 2L2 to something else, would you still have the same correspondence?
It has to be, so norms aren't strictly convex, right? Like a norm itself, like the L2 norm isn't. So it has to be a case where the squared norm is strictly convex, which I think that would be always the case, I believe.
Put the constraint form of that, like in the constraint, and just like limit the norm, and then somehow relating that parameter to 0.
Well, the relationship between, it's a little bit more tricky than that, because the relationship between this and its constrained form depends on the solution here. Right, so the constrained form bound that gives me the same solution to this problem depends on the solution, which in turn depends on epsilon. So it'd be like t sub epsilon. So it's a little bit more tricky than that, but let's see how I can explain this. So imagine that this criterion, which is true here, was jointly continuous in x and epsilon. Okay, so if I had the x epsilon plane, x is one-dimensional, then I should not expect somehow that like the minimizer as I move epsilon to jump around too much. So variational analysis just makes that precise. If you have a criterion that has some sufficient continuity properties as a function of like your optimization variable, but also some other variable which perturbs the criterion, here being epsilon. So it's just about continuity, not about convexity, because this is not convex in epsilon, x and epsilon jointly, right? But it's continuous in the two. Then I shouldn't expect the solution set to move around much. Or in other words, if I take slices of epsilon in that picture, then nearby slices should have similar minimizers.
Of course, when we looked at the convergence, like most of the times of the objective values, but you could also look at the iterates convergence,
Yeah.
right? So is there like sort of cases where you be careful in terms of
Yeah, that's a good question. So I would say generically, anytime there's strong convexity or more, we can always make statements about the iterates themselves. The solution is unique because strong convexity is stronger than strict convexity. So the solution is unique. And we have these bounds for strong. So strong convexity, we can bound the distance to optimality, right, between a point and x star in terms of the strong convexity constant. Went through a calculation like that as part of the Newton's method lecture, I think. So we can essentially translate things about f of xk minus f star to xk minus x star. Beyond that, the standard proofs for things, like for sublinear convergences, are in terms of criterion values. I think, if I'm not mistaken, the proofs for conversions to optimal points may even have slightly different or worse rates in some cases. Yeah.
Why do we always require the constraints to be convex? It feels like if you had a non-convex action constraint set, what goes wrong with
Well, so without a convex constraint set, we break the property that we can't have locally optimal, strictly locally optimal solutions. So here's an example. Let's suppose my constraint set was everything to this side and everything to this side, and I disallowed what's in the middle. So this is the constraint set. Then each of these points are locally optimal, which means that if I form a ball around these, they're better than every point in that neighborhood that's feasible.
Say you had a non-convex set that contained global minimum function.
The non-convex set contained a global minimum. So in that case, so if you're talking about if the non-convex set is open and the global minimum was in the interior, or let's say the interior wasn't empty, then you're in the case where you have a convex constraint set essentially. You've just added feasible points that are kind of extraneous. I guess we more or less operate under the assumption that the constraint set is convex because to make statements about like certain convexity properties, like I have something that underestimates the function, they have to have convexity. Otherwise, if you take, two points and you interpolate them, you could be infeasible. So a lot of the proofs of the stuff that we deal with, they invoke properties of convexity, right? Like the way we prove, for example, the most basic result for gradient descent is we invoke this result. The gradient's Lipschitz, so therefore we can write down an inequality like this. Now, if the constraint set was non-convex, then this could not be, that there may be some y's in x's for which this wasn't true, because we may have even left the domain of f. Right? I'm folding some other domain into the constraint set. So most of our theory, which uses properties of convexity, or implications of a smoothness property plus convexity, to arrive at a statement like this, they require to have a convex domain. I don't know if that was a good enough answer. I wasn't sure exactly what you were referring to or looking for. Is that a hand or just a... No, not a hand. Yeah.
Beyond second order methods, like let's say you were looking at third order, so there's two questions. One, is it true that you improve the rate from quadratic to like tertiary? Second, is there like a practical, like any application where you would consider that like a tensor type of thing?
This is an opportunity for me to say I don't know. I really don't know. I mean, I guess that means probably it's not major, but honestly I don't know. So you're asking, are there methods that achieve this kind of rate? So that's basically 0. I don't really know. Yeah, I mean, I wouldn't see if you gave me a third derivative, I wouldn't see what to do with it. Second order methods, I don't think of them as somehow being, it's not like odd to cut off the Taylor expansion at two derivatives to me, because a second order method, essentially once you differentiate, gives you a linear system, which are the things we know how to solve. Right? So
landscape, right? You're just like normalizing it properly. Yeah. So I just wondering like what's the next thing? I don't know. Just wondering.
So maybe the closest I can say is that self-concordance is something that ties the third derivative to the second derivative. And that's the case in which we know how we can understand second derivatives much better. We can understand second order methods much better. So for the sake of analysis, I guess there perhaps are cases in which it's helpful to know more curvature information. But for designing a method, I'm not sure. But even for self-concordance, like you tell me the third derivative is kind of nicely constrained by the second derivative, we still get this rate. I might look outside of optimization for answers to that question. Like I might look at what people do for like solving, for like discretizing PDEs. I might guess that somehow there they care about derivatives more, or like there's just more numerical analysis work that's done that looks at higher order derivatives.
Lower bound methods, like I think in the class we looked at the rates, but like what are techniques that go into improving lower bounds?
Techniques are, they're not as, they shouldn't be as mysterious somehow as you might first think. So let's just clarify what a lower bound is. Right. The lower bound says something like, just to paraphrase, this is Nestrov's lower bound. For any first order method, and any initialization, and any iteration in k that's not too large. So you can't look at k being like much bigger than the dimension of the problem, say, something reasonable. There exists a function f with Lipschitz gradient. So maybe with L Lipschitz gradient, and it's convex too, such that f of xk minus f star is bigger than or equal to something on the order of k squared. Right. So really what the proof is like, it's a very clever construction of a problem such that so first order methods, let's first recall what it is, and then I think I can explain the general proof strategy a little better. A first order method, it updates x, let's say k plus 1, in the span of x0 in all the gradients we've seen so far. So if we just use induction, we convince ourselves that gradient is sense in that class, right? Because I can write xk in terms of the span of xk minus 1 and this gradient. But then I can also prove that xk minus 1 is in the span of xk minus 2 and the previous gradient, etc. Right. Really what we have to do is design a problem such that no matter what iterates we visited, this sequence of linear spaces is going to be far away from the solution. So it's a specific construction. It's just a specific function he constructs. That if you give me any x0, I'm going to construct a function that's minimized at some x star, such that any sequence of linear spaces of this form is always going to somehow be bounded away from the solution by this gap. And its structure is it's actually quadratic, if I'm not mistaken. I think it's a quadratic. And It has to, I mean, there's some offset has to do with x0 or something like that, but the construction is something like this, if I'm not mistaken. It's like x transpose AX plus some stuff that involves x0, where A is very poorly conditioned. It's this matrix. I think this is, maybe somebody can look up Nestrov's construction in the meantime.
There's an extra term with x0, so like it's like x0 minus 1 squared.
X0? Oh, like this initial point, x0, minus the 1's vector?
Just x0 minus 1 squared. So it forces the first entry to be 1.
So x0 in the first component, minus 1 squared? What do you think?
Oh, yeah. Yeah.
Okay, but this must be somehow like if we chose the initial point x0 to be 0. Probably the proof says like it's translation invariant or something. But I guess what I'm trying to convey is that it's not, there's nothing information theoretic here. It's not like there's some construction that has to happen like on average for like a statistical lower bound. It's a specific function that's hard to optimize for any first order method.
What does the lower bound really inform you about the problem? Because like if you're looking at one particular problem and you're like citing the lower bound to say like you cannot do better, that's not really fair, right? Because the object you're solving might not be like one of those like.
That's right, but that somehow, but you have a statistician's cap on, right? So like a person, or a machine learning cap on. A person in operations research doesn't have a distribution over problems, typically, right? You ask about algorithms which have complexity over some class of problems. That's problems with Lipschitz gradient, and you know, the classic perspective is something like, you know, I just care about optimizing any problem to global optimality, and if any algorithm has some problem that's hard for that algorithm, then that's not a good case.
Class of objectives, like not in general, but
For class specific, I mean, this is a class specific lower bound. This is the class of objectives.
sure, but that's like, okay.
I mean, the closest thing I can think of to what you're asking for is a little bit far afield, but it's smooth analysis. So smooth analysis is, now we're moving a little bit away from our class, but it's still like a big deal for LPs. It started off for LPs, and this was Dan Spielman. I think it was also Shenghua Teng as well. I don't know what year that would have been, but basically the worst case complexity for an LP for something like the simplex method is exponential in the dimension. I think it's called the Clinty or Mi-Clinty cube. So there's a specific problem that the simplex method finds very hard. And what Dan Spielman and I think it was also Shenghua Teng did was that they looked at something like this. If you give me an LP, so something like this, minimize C transpose X subject to AX equals B and X bigger than or equal to 0. If you give me any C, any A, and any B, and you add Gaussian noise around them, small Gaussian noise around the entries of, let's say, A, X, and B, then what is the average case complexity if you start with an arbitrary C, A, and B, but add Gaussian noise? In that case, it becomes polynomial for the simplex. So I think it's a neat way of saying you don't have like a distribution over problems you care about necessarily because you're fixing arbitrary things in the optimization problem, but you're smoothing the problem in some sense by blurring these objects a bit. I don't know what that says for first order methods. Maybe somebody has seen work on that. I'm not really aware of it. And this is like still a very simple problem because it's a linear problem, right? Linear program. Let's take a break. When I come back, you guys can either continue asking questions, and we can even pivot to like review type questions if you want, or I can tell you about some non-convex problems. So let's take a couple-minute break. maybe it'll hit on several review topics. I just was asked to review dual ascent and how it relates to ADMM. So let's start off by just starting the problem of this form, and then deriving the dual, and then doing dual ascent, and then doing ADMM. So maybe that'll hit on some review topics. So the Lagrangian, right, is this guy. Right, which let's group terms in terms of this is A transpose U transpose X minus B transpose U. So that's the Lagrangian. And now what happens if I minimize the Lagrangian over X? What's the minimum of this thing over X? So how do we define the conjugate, let's say, of y of f? It's the max over all x of what? X transpose y minus f of x. Right, so if I took the negative conjugate of f at y, it's the min over all x of f of x minus x transpose y. I just put I had negative max, I moved the negative inside, I got a min, then I flip the signs of what are on the inside. So this thing here, so we minimize the Lagrangian over x, I get minus f star, because I get the minimum of this thing, which I know is f star, evaluated at minus A transpose U. Right? That is, that's my y in this equation. This is y transpose x. Actually negative this, right? Because I have minus y transpose x here, and I have plus A transpose U plus x. So y is negative A transpose U, which is why I'm evaluating the conjugate function there. And that's my dual function. Okay, so this is g of u. That's my dual. And now let's suppose everything's differentiable. F star is differentiable. I want to do something like this. U plus equals u plus t times the gradient of g of u. Because I'm operating the dual. The dual is a maximization problem. The dual is to maximize this. So this would be dual gradient ascent. Okay, what is the gradient of this criterion? What is this? You guys know the chain rule. Come on, this is the... Pretty sure you guys know the chain rule. Everyone's just really shy. Is it A? Yes. And then this is grad of f star minus A transpose U minus B. Yes. See, I don't know how to compute derivatives either. Okay, so we almost know how to compute the gradient, except for we don't know how to compute, let's say, the gradient of f star, and that's where this relationship comes between subgradients of functions and subgradients of their conjugates, which actually Aditya invoked in the last lecture, and some of you guys may have missed that. His statement about the inverting the mirror map was that same fact. So let's recall that. So fact for closed and convex functions, x is in the subgradient of f at y if and only if y is in the subgradient of f star at x. And let's suppose that, so a special case is when f is strictly convex, which means that f star is differentiable. Okay, this becomes x in this, let's see how I can write this. This becomes, well, okay, let's first write it like this. X in the subgradient of f at y, if and only if y equals the gradient, because there's only one subgradient when this guy is convex and differentiable. Okay? And, okay, let me just first maybe explain to you what I said about Aditya's lecture. If f was also differentiable, so if f is, let's say, has ellipsis gradient and it's strongly convex, then that's true if and only if the same is true of its conjugate. And let's say if we throw in differentiability, that's also true if and only if its conjugate satisfies all those properties. So if we're in a situation where it has enough smoothness, if f is also differentiable, then this statement looks like this. X equals the gradient at y, if and only if y equals the gradient of the conjugate at x. So what does this mean? This means that the inverse of the gradient, just write it as an operator. The inverse of the gradient map is the gradient of the conjugate. This is not supposed to be anything here. This is just supposed to be gradient of the conjugate, right? This is saying that if I apply the gradient, then I apply the conjugate, I get back x. So this means that the inverse of the gradient map is the conjugate, is the gradient of the conjugate, which is what he was claiming in his lecture. So that just comes out of a special case of this rule. What we care about is a slightly different implication. Right, so I'm trying to think about what's the easiest way to do it without going through the proof. So x being a subgradient at y, x being the subgradient at f of y, it means that y equals the argmin over all z. See if I get this right or if I get it backwards. Of f of z minus x transpose z. Okay, I claim these two are equivalent. So let's just do subgradient optimality here. If I take a subgradient with respect to z, and I know the minimizer is y, I get that 0 must be in the subgradient of f at y minus x. Right, which is, so this is subgradient optimality, which is the same thing as saying that x must be in the subgradient of f at y. Okay, so this is equivalent to this, and this statement is equivalent to having a gradient of our f star. So now we use the equivalence between this and this to derive the update rule here. So now we say that the gradient of f star at the point minus a transpose u is equal to the argmin, let's say over all z, of f of z plus u transpose az. All right, that's just using this equivalence up here to compute the gradient. And now the gradient of g is just, I get by assembling somehow the chain rule with that last fact. So then gradient, dual gradient ascent looks like x plus, I first minimize, let's say, over all z, f of z plus u transpose az. And then I just, I do u plus equals u plus some step size times the gradient. And looking back at what we did for the chain rule here, it's going to be a times x plus minus b, right? Because x plus was this thing here. A times x plus minus b. Okay, so we hit upon, I guess, some various topics there. All right, so that's dual gradient ascent. ADMM is just a problem in which ADMM, suppose that, let's say, first of all, x was a block variable. We'll call it maybe u. No, I shouldn't use u. I just use the dual. I don't know, w comma v. So we have a block variable. And well, I also use w and ADMM for the scale dual. That's not good. You guys are going to look back at the notes and get confused. Suppose, let's say, x is replaced by x comma z. So there's two variables. There's a block decomposition rather than just one. And I augment the criterion. Augment the criterion by, you know, something of this form. If I had an equality constraint that looked like ax plus bz equals c, right? Where now I'm expanding the equality constraint we had into something of this form. I augment the criterion by that. Then the only difference between dual ascent and ADMM so this one computes the full gradient. Which means that we actually do this with my new kind of expanded variable xz, and this, you know, be replaced by this as it would be plus this augmented term, and ADMM actually splits that into two. Splits up the min over x and z, which is a joint minimization, into two steps. So it doesn't actually give you the gradient per se. It's not actually doing gradient ascent, but we know that it has convergence properties. Okay, that was the motivation that led to ADMM. And if you go back to the lecture slides, there's probably it's better for me just to tell you, look at that one slide that you can see. I write down explicitly that there's ADMM, which does min over x, min over z, then this dual update, and then there's the dual method, which does min over x and z, then the dual update. Yeah.
So if you take this, the conjugate as the mirror map, how does the mirror descent come into play?
If I take the conjugate as the mirror.
Where you have like the inverse gradient map, like you could use it as a mirror map, right, for mirror descent, right, or just generally for mirror descent, like to the inverse gradient.
Yeah.
Right, it's like we have the mirror descent, right?
Yes, that's right.
So how does that like tie together with ADMM there? Is it more like standard gradient descent with different distance metric?
So the difference is that, and somebody asked us on Piazza, and I gave kind of an answer there, but I'm happy to repeat it or elaborate here. The difference is that so mirror descent never touches the Lagrangian dual. So mirror descent, you define, so you're given f, right? Then you define some mapping phi. And you perform a step that looks like this, right? Phi of x minus grad f of x. And then you take the inverse of grad phi, which is grad of phi conjugate. but you never touch the Lagrangian dual of your problem, and so you never see any F stars appearing here.
If my phi is actually mapped to the dual space, like what would be the interpretation be then if I were to compare?
So they're both uses of the word dual. They're both actually like common uses of the phrase duality, but they're not the same. So, and a lot of these are related. So every time you see duality and optimization, it's usually related to Lagrangian duality. So you'll see lots of different formulations of duality, like ventral duality. It's a special case of Lagrangian duality. So having taught you Lagrangian duality, I would say that kind of supersedes everything. The dual you're seeing here, when Aditya said that there's a space and then there's like a dual space that this is mapping into, grad phi, that's not Lagrangian duality. This is a duality in a functional analysis sense. So in our case, somehow, like if we're talking about optimization Euclidean spaces, these are the same space. This is Rn, that's Rn. But in a more general setting, like suppose you're minimizing over functions. So your x was actually a function. It wasn't a discrete variable, or wasn't a variable in Euclidean space. It's a variable in some like functional space. Then if that functional space was called F, then the dual is called F star. And this dual, it is defined as the set of all linear maps from F to R, to the real value, to the reals. And the gradient is what takes you to this dual space.
So even if I were to pick phi as the like conjugate function, it would not really be the dual in that sense. That would be like every similarity would be kind of coincidental.
Yeah. I mean, there's probably more connections than that, but I would just think about them as different uses of the word dual. I mean, I think that we could probably draw some more connections, but it's probably less helpful to draw those until you learn more about duality in other senses. Like mirror descent in Euclidean space is not actually moving you to like a different space. It's still Rn. We have a few minutes, 4 minutes.
Dual method, and there we use proxy for the duality gap.
Yes.
And so how do we know that it's going down? Is there like some theoretical guarantees or something that it's going down?
Yes. We didn't really do any theory for primal dual and terabyte method. So yes, there's theory for it, and I think one has to be careful about how you do backtracking. But the version some of the formulation I gave you in class, I think I can feel kind of confident to say that's convergent. But like if you wanted to look at a specific theorem, then you'd have to look outside of like Boyd and Vandenberg as well. And there's a book that Stephen Wright wrote called Primal Dual and Cherry Point Methods. And there I'm positive that you can find a theorem that says that with a particular update for primal dual and cherry point method, you get that the residual gap and the duality gap goes to 0. So yeah, sorry, not a great answer, but there is theory, we just didn't really cover it. Okay, I guess there's no point in keeping you guys here. You guys can take a look at this guy right here. It's way too many slides, but you might find a problem here that you're interested in. And my usual thing is that if you think of a problem that should be here, you can let me know about it. I'd be happy to put it in. I've just kind of added to this over the years of examples of non-convex problems that are not impossible. So maybe you want to look at this after the little test in case you don't want to, mess up your understanding of convexity too much. But thank you guys. I will see you. I won't be here for the little test. I will see you guys next Monday for COPS.